Efficiency, precision, and quality are not separate goals in a modern smartphone factory. They are the same goal, pursued through a tree theory of the law of the product. It is evidence of what modern manufacturing, at its best, is capable of achieving. In its glass surface, the factory itself is reflected, a quiet reminder that this object did not simply appear. It was designed, sourced, machined, assembled, tested, and approved by a system of extraordinary complexity and discipline. What looks simple in the hand is, in every way, remarkable.
Every smartphone that reaches this point has traveled an extraordinary path. More than 70 materials, hundreds of individual components, thousands of assemblies.
As day shifts to dusk, the factory does not stop. Production lines continue through the night. Automated systems maintain their vigil. A machine and
Artificial intelligence is increasingly integrated into quality inspection systems. Machine learning models trained on millions of images can detect defects subtle and subtle rates that human fractions of not miss. The factory grows more precise with every device it produces. Modern factories are not purely automated, nor are they purely human. They are a carefully calibrated collaboration between the two. Collaborative workers contribute tasks that demand perfect consistency and dialogability. From this elevated perspective, the full scale of the operation becomes clear. Dozens of production lines, hundreds of workstations, will put machines and portraits into a single market. Behind the visible activity of the production floor, a vast system of data underpins every decision. The factory's manufacturing execution system tracks every component, every assembly step. Pallets are loaded into freight trucks at the factory's loading bays. Some will travel by road to regional distribution centers. Others will move to airports where they will be loaded onto freight aircraft. Manufacturing journey is over. The distribution journey has begun. At the dispatch bay, each pallet is scanned one final time before it leaves the facility. The scan updates the factory systems, confirming that this pallet containing these specific devices has been released from the facility and is entering the distribution network. Wrapped pallets move into the finished goods warehouse, the final station before distribution begins. In this warehouse, the output of the entire factory accumulates, waiting for the logistics chain to carry it outward. Each completed pallet is wrapped in multiple layers of clear stretch film by an automated wrapping machine. The film binds from moisture, dust, and the small movements that accumulate over thousands of kilometers of freight travel. Master cartons are stacked on pallets by a robotic palletizing arm, arranged in an electronic pattern and distromizes structural stability. The pattern is not arbitrary, it provides this freight transport. Individual device boxes are grouped into master cartons for shipping. Each master carton is sealed, labeled device trail and assigned to travel as a group, but each one retains its individual identity within the logistics system. A label is applied to the outside of the sealed box containing the device's serial number, IMEI code document, and the information it carries must correspond exactly to the records held in the factory's quality database. The box is engineered with the same attention to dimension and tolerance as the device it contains. It must hold the smartphone securely, prevent any movement during shipping, protect the contents from impact, and project the quality that the device itself represents. A charging cable and any other included accessories are laid neatly into their dedicated compartments within the box. Documentation is folded and placed precisely. Each item has a defined position, a carefully considered arrangement that the customer will encounter the moment they open the box. The box is engineered with the same attention to dimension and tolerance as the device it contains. It must hold the smartphone securely, prevent any movement during shipping, protect the contents from impact, and project the quality that the device itself represents. The approved, cleaned, and film-protected device now moves to the packaging line. Here, the smartphone is placed into a precisely formed inner tray, where the molded contours of the packaging hold it securely in position. Every accessory that will accompany the device is staged and ready. A fresh protective film is applied to the display, this time for the benefit of the customer. It will protect the glass from scratches during shipping and handling, and it will be the first thing the device's new owner peels away when they take their phone out of the box for the very first time. The protective film applied to the display at the beginning of assembly, the film that has shielded the glass surface through every step of the manufacturing process, is now removed. Beneath it, the display surface is perfectly clean and undamaged. Devices that require cleaning are wiped with lint-free cloths and specialized cleaning solutions before reinspection. Fingerprints, dust, and assembly residue are removed from embrace, the camera lens covers. Everything must be spotless. By holding the device at a raking angle beneath a bright directional light, the inspector can detect scratches on the glass, marks on the aluminum frame, and any gaps or misalignment between the display and the chassis. Functional performance alone is not sufficient. Every device must also meet strict cosmetic standards. Human inspectors examine each unit under multi-angle lighting, kits designed to reveal surface imperfections that straight-on illumination would never expose. Every single test result, every number, every pass, every failure is automatically recorded against the device's unique serial number. This creates an unbroken digital record of every test ever performed on every device that passes through the facility. The final stage of functional testing evaluates the device's water resistance. A controlled stream of water is directed at the device from a calibrated nozzle, simulating the conditions defined by the device rating ingress, and then it must continue to function perfectly. The device's motion and environmental sensors are calibrated against reference standards. The accelerometer, gyroscope, compass are measured and compensated for through calibration data written into the device memory. Biometric systems are enrolled and tested at a dedicated station. The fingerprint sensor must verify a registered sample within a defined response time and must reject unauthorized acceptance. Cellular connectivity testing takes place inside a shielded enclosure that isolates the device from real-world radio signals. The test system simulates the radio frequency environment of a live network. Audio testing takes place inside a small anechoic chamber, a box lined with sound-absorbing foam that eliminates a mobile and distortion. The noise cancellation performance of the microphone array is also verified. The analysis software produces a detailed report for each camera module. Charts. Video recording is also tested. Stabilization, autofocus tracking, and the synchronization between the audio and video streams are all evaluated. Camera testing takes place inside a small, calibrated photographic test booth. The device's cameras photograph a standardized test chart under controlled lighting conditions. The resulting images are analyzed all automatics. Touch responsiveness is tested across the entire screen surface by a robotic probe that contacts the display in a systematic grid pattern. Every point that registers correctly lights up green on test display map. A single unresponsive zone anywhere on the screen is sufficient to fail the device. Display testing evaluates brightness, color accuracy, contrast ratio, and uniformity across the full screen surface. The display cycles through solid white, solid black, and each one revealing different aspects of the panel's performance. The device now enters a comprehensive testing sequence, a series of dedicated stations, each designed to evaluate a specific set of functions, temperature, battery, before the device is allowed to proceed. When the software is fully loaded, the device reboots and launches its operating system for the very first time. The screen that lights up in this moment is the same screen the device's eventual owner will see, a clean, fully configured system ready to be tested. The flashing process can take several minutes, depending on the volume of software being written. During this time, the device's unique identifiers are also programmed, its serial number, its IMEI codes that identify it on cellular networks worldwide, and calibration data specific to its individual components. Before functional testing can begin in earnest, the device must receive its software. Each phone is connected to a high-speed flashing station where the operating system, pre-installed applications, and factory configuration data are written directly into the device's storage memory. The physical assembly is now complete. The assembled device is placed into a functional test fixture where contact pins engage its test interface. What follows is not a simple pass-fail check, but a comprehensive evaluation of every function the device is capable of performing. Rubber gaskets are fitted around the charging port, speaker grills, and any other openings in the chassis where water could potentially enter. Waterproofing mesh, allowing sound to pass freely wide microphone openings. Together, these seals give the device its rated water resistance. An automated pressing fixture applies precisely calibrated even force across the entire display surface, compressing gasket uniformly around the perimeter. Uneven pressure could leave weak points in the seal, areas where moisture or dust could eventually find a way in. For devices that pass the initial check, assembly continues. The front display module, the OLED panel bonded to its protective glass, is carefully aligned with the sprayed and lowered in position water. A temporary test display connected to the device shows the results of the initial power on check in real time. The processor, memory, storage, and core circuits are each verified that this stage is removed from the line immediately and directed to a diagnostic workstation for investigation. With the battery connector pressed home, the device receives power for the very first time. This first power on does not happen after assembly is still open. Firmware on the logic board runs an immediate verification check to confirm that the core electronics are functional inside the chassis. This adhesive provides both secure retention and a degree of vibration isolation. The battery is oriented carefully, its connector positioned to reach the logic board's power socket without stress on the cable. The earpiece speaker and the main speaker module are seated in their designated locations and connected to the logic board. The vibration motor, small component that to feed bass, may work intermittently or not at all. Camera modules are inserted into their apertures in the chassis and secured in place. A ribbon cable connects each module to the logic board. The alignment between the camera's lens and the opening must be exact. Any tilt or offset would be visible in every photograph the device ever produces. Flexible ribbon cables connect the logic board to buttons, sensors, and secondary circuit boards distributed throughout the chassis. These cables are routed through narrow channels with great care. A pinched or sharply bent cable may pass visual inspection but fail prematurely in the hands of the customer. Each screw that secures the logic board is driven with a calibrated electric screwdriver that automatically stops the moment the correct torque value is reached. The result of every fastening operation is recorded in the factory's quality system. Too much force could crack the board, too little could allow it to shift. The main logic board, the PCB carrying the processor, memory, and all the core electronic systems, is lowered carefully into the chassis. Connectors align, the board settles into its mounting position, and for the first time, the device begins to take its final form. Antenna strips are laid carefully into channels routed into the interior of the frame. These antennas will allow the finished phone to communicate across multiple wireless frequencies, cellular networks, Bluetooth, and GPS. Their precise placement directly affects the device's signal performance. Assembly begins with the chassis. Thermal interface pads are placed at specific locations in the octamed interior, all soft and dynamic to the metal frame, participate safely. With all the major components prepared, the logic board, display, factory now moves into its most visible phase, final assembly. This is where all the individually manufactured components converge into a single, unified device. The visual character of the phone's back is created by printing color and decorative layers onto the inner surface of the inside, so it acts as a protective transparent layer over the color, giving the finished surface a depth and richness that paint on a solid surface cannot replicate. Many smartphones feature a glass back panel, not merely for aesthetics, but because glass is transparent to the wireless charging frequencies that pass through it, each precisely sized to fit the device's chassis. After anodizing, the frame receives its final color, achieved by absorbing dye molecules into the porous oxide layer before it is sealed. The result is a surface that is simultaneously hard, corrosion-resistant, and richly colored. As the frames are lowered into the electrolytic solution and an electrical current is applied, tiny bubbles rise from their surfaces, the electrochemical reaction transforming the aluminum. The oxide layer being formed at this moment is harder than the base metal beneath it. The frames now enter the anodizing line. Hundreds of frames hang on titanium racks, suspended above a series of large chemical treatment tanks arranged in a precise sequence. What emerges from the machining center is a precisely formed aluminum frame, every edge sharp, every opening dimension to the disc. This stage, the frame has a raw, machined appearance. The surface treatments that will give it its final character have not yet begun. Inside the machining center, cutting tools carve out the display opening, camera apertures, button channels, and port openings with finely cut across as the fine limb. The structural backbone of the smartphone, its chassis, is typically formed from aerospace-grade aluminum alloy. The manufacturing process begins with solid billets of aluminum loaded in computer-seam shading metal. Completed battery packs are stored in dedicated fireproof cabinets until they are needed on the assembly line. Temperature is monitored continuously, the number of batteries held in any single area of the furnace, and the energy they contain. The protection circuit acts as the battery's guardian, preventing overcharging, over-discharging, and short circuits under any operating conditions. Without it, the energy storms a safe, reliable power source designed to last for years. The protection circuit module is connected to each battery cell using spot welding. A process delivers a precise burst of electrical current to cell beneath to create a strong bond while monitor the battery voltage and temperature for the entire life of the device. The battery is one of the most carefully handled components in the entire factory. Lithium-ion cells store a significant concentration of chemical energy, and their handling is governed by strict protocols. Only those with tested for high risk range are accepted. Every completed camera module is tested against a standardized optical test chart. Focus accuracy, exposure performance, color rendering, and image stabilization are all evaluated automatically. Only modules that meet every specification are cleared for installation into the phone. The lens with a violet is in use moment forward. The optical relationship between the lens and the sensor is fixed, precisely as calculated, and impossible to alter without destroying the module. While the alignment is in progress to the investor, the system continuously captures test images and analyzes their sharpness, adjusting position until the image quality reaches its peak. Inside each camera barrel, a stack of optical lens elements works in combination to produce a sharp, distortion-free image. Each element has a specific curvature or fragmented element would degrade every photograph the camera ever takes. The camera system is one of the most technically demanding components in the entire device. What appears to be a simple cluster of lenses is, in reality, a sophisticated optical instrument assembled with precision that rivals the finest watchmaking. Touch responsiveness is verified across every point of the screen. A robotic probe systematic from a precise grid pattern, timber touch digitizer detects input accurately at every location, from the center of the screen to its most distant corners and edges. Each completed display module is tested extensively before it proceeds to final assembly. Automated test equipment cycles the screen through a full sequence of solid colors and pattern-seeking and patterns. A powerful ultraviolet light source then cures the adhesive in seconds, locking the glass and the OLED panel into a permanent, optically seamless bond. What were once two separate components are now a single unified display assembly, inseparable and perfectly aligned. The bonding process takes place inside a vacuum lamination machine. With all air evacuated from the chamber, the protective glass cover is pressed onto the OLED panel. The vacuum environment ensures that not a single air bubble can become trapped between the two surfaces. An optically clear adhesive is applied uniformly across the OLED panel's surface. This adhesive must be absolutely free of stage, would create a permanent visual flaw in the finished display, visible to every user who ever looks at the screen. Modern smartphones use OLED technology, organic light-emitting diode panels. Each individual pixel generates its own light, producing the deep blacks, vivid colors, and ultra-thin profiles that define today's premium displays. Display assembly takes place in a clean room, one of the most controlled environments in the entire factory. The air here is filtered to remove particles as small as a fraction of a micron. Workers wear full clean room suits to prevent any contamination from reaching the delicate display surfaces. For the boards carrying the main processor chip, an additional step is required. X-ray inspection penetrates the board through a grid of tiny solder balls hidden beneath it in visible proper contact with the board below. Every board that exits the reflow oven is immediately inspected by an automated optical inspection machine. High-resolution cameras mounted on precision gantries photographs lenses missing camera. Inside the oven, the solder paste melts and flows, creating permanent electrical and mechanical bonds between every component and the board beneath it. As the boards exit the oven to the cooling section, solidifies, and with it, every connection is locked into place. The populated boards then enter the reflow oven, a long, tunnel-like machine divided into precisely controlled heat zones. As the boards travel through the oven on a slow conveyor, the temperature rises gradually through a carefully programmed thermal profile. As the board travels down the SMT line, it becomes progressively more populated. What began as a blank gray-green panel is gradually eroded the device's intelligence, waiting to be permanently connected. Some of the components being placed are almost impossibly small, resistors and capacitors smaller than a grain of salt, yet each one in precisely the right orientation and exactly the right location. Next, the boards enter the pick-and-place machines. These robotic systems use vacuum nozzles to pick individual components from supply reels and place them onto the solder paste deposits with extraordinary speed and accuracy. The fastest machines can place tens of thousands of components in a single hour. When the stencil is lifted away, it leaves behind a perfect pattern of solder paste deposits, hundreds of tiny gray dots, each one precisely placed, each one waiting to be a component. Even the slightest misprint at this stage would result in a flawed solder joint further down the line. The first step is solder paste printing. A thin metal stencil, a squeaky blade pushes solder paste wacha through the openings, depositing exact, tiny amounts of paste at each designated position. With the bare boards prepared, they enter the surface mount technology line, the SMT line. This is where the board truly works in perfectly combined. A modern smartphone circuit board is not a single layer. It is a day-old layers of volatile metal, just a millimeter or two thick. Each layer must align with every other layer to within a fraction of a millimeter. After etching, the result is extraordinary. These traces are the highways of the smartphone's nervous system, carrying every instruction and every piece of data the device will ever process. A photographic process called photolithography transfers the circuit design onto the copper surface. Ultraviolet light is projected through a precision mask. Where the falls on the copper will remain. Where it does not, the copper will be etched away. Each laminate sheet is coated with a thin, uniform layer of copper. This copper will eventually become the circuit traces, the microscopic pathways along which electrical signals will travel at the speed of light, connecting every component on the finished board. The heart of every smartphone is its printed circuit board, the PCB. Manufacturing begins with sheets of fiberglass reinforced epoxy laminate. This screen is the physical foundation upon which the entire electronic brain of the device will be built. When a production line sends a request for components, automated guided vehicles respond. These low, compact robots navigate the warehouse floor using magnetic tracks or laser guidance systems, collecting and silently, efficiently, without interruption. Approved components move into a carefully managed warehouse where temperature and humidity are continuously controlled. A single humid day in storage could silently compromise the performance of thousands of components. Before any component is accepted, it must pass incoming quality control, known as IQC. Automates are verified, surfaces are checked for defects, and electro-character plier immediately. Components are laid out on inspection tables under bright, even lighting. Display panels, camera sensors, processor chips, battery cells, and communication modules, each one sealed in anti-static packaging to protect against the invisible danger of electrostatic discharge. The moment a shipment crosses the threshold, it is logged. Every box, every batch, every individual component receives a barcode scan that registers it into the factory's central inventory system. Nothing enters this facility without a digital record being created. Pallets wrapped tightly in protective film are lifted from the containers and moved onto the factory floor. Each pallet represents a carefully planned delivery, timed to arrive exactly when the production line will need it, not a day too early, not an hour too late. The journey of every smartphone begins not on a production line, but at the receiving dock. Climate-controlled freight containers arrive around the clock, carrying the raw materials and pre-manufactured components that will become the device in your pocket. Somewhere on the outskirts of a modern industrial city, behind clean glass walls and quietly humming ventilation systems, one of the most complex, this is a mega factory, and inside it, smartphones are born.